scalar projections and vector projections. This is interesting. Let's see. Well, everything is interesting. This is math. Now, let's say we have a vector here. We're going to call it vector A. And then we have another vector going this way. And this is going to be called vector B. And it happens that sometimes these vectors are separated by a certain angle. And we're interested into the effect of the first angle of the first vector, onto the second vector. Or what is the component of the first vector onto the second vector? Or the mathematical word, the projection of vector B onto vector A. When I say projection, imagine that we have a light bulb or the sun here. What is the shade caused by this vector B onto vector A? What is the length and direction of this vector? Okay, this vector right here, we're going to call it the projection of vector B onto vector A. We're going to calculate that projection. So to do that, first let's do some scalar projection, like how big is the vector going to be. Okay, so let's call this for now the component. Actually, no, we're not going to do that. This is what we're going to find out. What is the component of that vector B, of the projection onto A? How big it is. Okay, that's what it is. How big is this vector? And then we're going to deal with the direction. But how big the vector is? Well, we know this vector is going to be, as we learned a few years ago, this is going to be B times cosine of theta, right? That's a nonsense. That's really easy. Now, we just learned that the cosine of theta is what it is, times, actually, this is the magnitude of B, not just the vector B. The cosine of theta is vector A times vector B, is the dot product of A times B over the magnitude of A and the magnitude of B. Okay, so now we have the magnitude of B times cosine theta. That's what it is. And now we're going to cancel out the magnitude of B, and we know the length of the projection of B onto A, or the component, is the dot product of A and B divided by the magnitude of A. This is the length of this orange vector. Okay, now we're going to deal with the direction, the length of our magnitude. Now, to deal with the direction of this vector, so we know the direction is the same direction as vector A, and the direction of vector A is given by its unit vector. Let me write that down. The direction of A is given by its unit vector, and the unit vector is given by, as you know, A over the length of A. So the vector projection, what we're looking for, the vector projection of B onto A is going to be the magnitude that we just got in orange, which is going to be A, the dot product of A and B over the magnitude of A, times the unit vector of A that gives us the magnitude. Okay. And this is going to take us to the final formula. The projection of B onto A is going to be the dot product of A and B over the square of the magnitude of A. This is just a number that we're going to multiply by the vector A. Now this number is interesting, that this vector is interesting because the number, the magnitude of this projection might be half of vector A, okay? Like in the example. 1/2 of vector A could be 1/3 of vector A, could be 0.01 vector A, could be 3 times vector A, could be negative times vector A. That will happen if B is going in the opposite direction, and so on and so forth. Okay, so I'm gonna stop now, and we're gonna do some exercises about this. Have a great day. I'll see you later. Bye.